Here's some homework help for the problems on pages 259 and 260. This is from section 5.4, and this whole section we're reviewing factoring. And we discussed in class today what factoring really is. It's rewriting an expression using the multiplication of two or more factors. So the thing to keep in mind when you're factoring, and just train yourself to think this way, you should always ask yourself, is there a GCF? That needs to be the first thing that you check for in any factoring problem. Well, for number 12, the answer to that question is no. So now I'm going to look for another way of factoring, and since it's a trinomial, we discussed how that we can, in certain cases, express trinomials, quadratic trinomials, as the product of two linear binomials. Okay, linear meaning each of these binomials will have x to the first in them. And that should make sense because when you do the FOIL method, you multiply these first terms together. X times x will give you x squared from the trinomial that you're supposed to factor. Now these next two, the second two of each binomial, the second two terms, need to multiply together to give us 40. But they also have to add to give us 22. So the way we express this is we're looking for the multiples of 40 that would add to 42. So if you're not sure about that, just start making a list. Start simple. Obviously 40 times 1 is 40, but these two numbers added together do not equal 22. So we'll keep looking. 20 times 2 multiplied together, if you multiply this, that's 40. And if you were to add those two terms together, 20 plus 2 is 22. So we have found the factors of 40 that add up to our linear coefficient of 22. So those are the numbers that go in the other parts, these other numbers of our answer. And I could have switched these. I could have put 2 here and 20 here. That doesn't matter. Everything is positive in the trinomial, so that means everything is positive when I write my two linear binomial factors. And I would recommend, if you want to make sure you're right, you can use the FOIL method. That's how we multiply two binomials together, and if you use FOIL on these two blue linear binomials, then it should equal the original quadratic trinomial. Okay, so there's your answer for number 12. All right, the same idea on number 18. Look for a GCF always, and just ask yourself the question, do I have a GCF? And the answer is no. Okay, so the next best thing is, can this trinomial, this quadratic trinomial, be written as the product of two linear binomials? Well, let's see. Obviously, linear means I'm going to have x to the first in each group, each binomial. Something interesting here that did not happen in this number 12, you may have learned in Algebra 1 that if in your trinomial you have a minus sign in front of a plus sign, okay? Well, that takes care of my signs in the two binomials, the two linear binomials. This is always true, that if you have a minus sign that precedes a plus sign like this, then both of your signs in your factored answer have to be minus. And if you think about it, that makes sense, because remember when we do this last part of FOIL, these last two terms have to be multiplied together. So in order for that to become positive when multiplying, then we must be multiplying two negative numbers. Okay, so I'm just going to go ahead and put the two minus signs, and now I'm looking for the factors of 36 that add up to, I'm just going to call it 13 since we've already taken care of what the signs are going to be. So again, if you don't see it right away, just start working your way through a list. 36 times 1 equals 36, but if I add those together, that does not equal 13. So I'm going to keep looking. I know that 18 times 2 is 36, but if I add 18 and 2, I get 20. So that's not going to work. Let's see, what else? I know that 12 and 3, 12 times 3 equals 36, but if I add those together, I get 15. So that's not going to work. So keep working down my list. I know that 9 times 4 is 36. And if I add those together, I do get 13. So I have found the two factors that will occupy these two positions, and it really doesn't matter in which order you put them. You could have put 9 here and 4 here. So that's your answer. Again, to have confidence, use FOIL. I'm not going to require it. I'm just going to say, if you miss these, then you need to get mad at yourself, because you could have known if you were correct just by using the FOIL method, which would take about 5 or 10 seconds, maybe less. Okay, let's keep working through. Again, I just want to make this question part of your factoring process. Is there a GCF? Well, there is not. All right, so my next question would be, can I factor this quadratic trinomial as the product, which is another word for multiplying? Can I multiply two linear binomials together? And when I do, using the FOIL method, would I get this red quadratic trinomial? So some people call this process that we're doing now unfoil, because if we actually do the multiplication, we should get this. So we're kind of working backwards. We're taking the trinomial and trying to come up with what would be multiplied using the FOIL method. Okay, so if it can be factored as two linear binomials multiplied together, then there will be factors of negative 63 that add up to positive 2. Okay, so I won't go through the whole list. I think you got the picture from my previous example. But I do know that 9 times 7 is 63. Now this needs to be negative 63, so one of these numbers to make negative 63 will have to be negative. One of them negative, one of them positive. But I've got to keep in mind that when I add these two together, I'm supposed to come up with positive 2. Okay, so that helps me with my signs. In order for these two added together, first of all, I need to make negative 63, and now I'm trying to come up with which one of these is negative. One of them has to be. Well, to make it become positive 2 when adding, then that means the 9 has to be positive. It's bigger. 9 plus negative 7 is positive 2. Okay, so that helps with the way the factoring looks. I'm going to have positive 9, or plus 9, and minus 7. And once again, if you already did this problem, if you turn these around like this, that's certainly okay, because multiplication is commutative, meaning that we can change the order of these factors and we will get the same result. Okay, let's try number 24. Is there a GCF? No. Okay, now let's see. Can we use two linear binomials multiplied together to represent this quadratic trinomial? Linear means that we're going to have t to the first in each binomial. So if it's able to be factored, then there must be factors of negative 44 that add up to negative 7. So you can work through your list. Negative 44 times 1 and 44 times negative 1. Both of those equal negative 44 when multiplied, but neither of them when added would equal negative 7. So you could try 22 times, or negative 22 times 2 and vice versa, but that's not going to work. So it looks like the factors 11 times 4, I recognize that 11 times 4 is 44, but I've got to make it negative. So I'm on the right track here, because remember, when I add these two together, I'm supposed to come up with negative 7. So it's just a matter of placing the signs correctly on these two factors, so that when I do add 11 and 4 together, I'm going to come up with negative 7. Well, that means that the 11 must be negative. 4 must be positive, because a negative 11 plus 4 is negative 7. So my factoring will be t minus 11. That's one of my linear binomials, and then t plus 4 is the other one. And again, just like we saw up here, you could have switched these complete binomials. Now, don't switch the signs, but if you switch the binomial order, then that would be okay. All right, when we get to number 26, 26 and following, notice that these trinomials are a little different, and what makes them different is this a term. Remember, this is just standard form. We have a in front of x squared, b in front of x, and then this number is our constant, or c. So when a is not 1, we are going to have a little different way of going about the factoring, and I want you to use this, what I'm calling the box method. I want you to show it just for the problems, and there really aren't that many, but any of your trinomials where a is greater than 1, then I want you to show this method that I'm showing you in class, and I just call it the box method. Some of you have seen this in Algebra 1. Well, first of all, let's go back to what we talked about earlier about signs. Do you remember in our previous problem, a couple of problems ago, we had in our trinomial minus preceding plus. Okay, well, let me back up. I'm getting a little bit ahead of myself. Do we have a GCF? That needs to be the first question we answer, and the answer is no. So now I'm left with, okay, can I represent this quadratic trinomial as two linear binomials multiplied together? Well, now let's go back to signs. Remember what this means? Minus in front of plus in the trinomial. That means that I know what the signs of my answer have to be. Both of these binomials have to contain minus signs. Okay, so now let's get into, now that we know what the signs are going to be, then we will not worry about signs when we go to this method that I'm calling the box method. The signs have already taken care of themselves. So when I go to put numbers in this particular case, I'm just going to use all positive numbers, and we're just going to plug in the results as they come out of our box method. Okay, so here's how the box method works. Your first step is to look at your first term, which is 2x squared, and your last term, which is 24. And you're just going to place them across from each other diagonally, and it really doesn't matter how you go, but I just always place them diagonally in this way. Okay, so step one, take the first and the last and place them in these two squares. Okay, step two, let's multiply those together. I'm just calling this step 2 here. Just take those two terms that you wrote down in the box and multiply them together. Okay, so step 3 is the one that's going to probably cause you the most thinking. So what we're doing in step 3 is look at this product, 48x squared, and see if we can determine what the factors of this product are that would add up to 19x. Remember, in this case, I'm not worried about it being negative. The signs are all taken care of. So in this scenario, whenever you have minus in front of plus, just don't worry about coming up with, don't worry about using negative numbers. That's already taken care of. So I've discovered that the factors of 48x squared that add up to 19x are 16x and 3x. And I'm just going to place those in the other squares. And I could have switched these. There's no magic to one of them having to always be placed in a particular square. These could be switched. Okay, now our last step in this process will be to find there are 4 GCFs for each of the rows and each of the columns. I'll just try to squeeze them in here. So these blanks represent where I'm going to place the GCFs of each row and each column. Okay, let's see what we get. This top row, the GCF would be 2x. This bottom row, the GCF would be 3. For this first column, the GCF would be x. And for this column, the GCF would be 8. 8 is the largest number that goes into 16 and 24 evenly. Okay, so what we've shown here are the 2 binomials that will represent our factoring, the 2 linear factors. Okay, one of them will be 2x minus 3, and the other one will be x minus 8. Okay, so just want to point out again, when minus precedes plus and you're using the box method, just go ahead and put the 2 negative signs, the 2 minus signs that will appear in your answer, and then you don't have to worry about using any negatives at all in your box. Okay. Here's another one, very similar. I'm looking for GCF first, and don't see one. So now, since A is greater than 1, I'm going to use the box method. So again, do not use the box method unless A is greater than 1. It's going to take more time than is necessary. Okay, so let's walk through the box method again. First term, last term. Okay, step 2, multiply those together. All right, step 3, I need the factors of 72x squared that would add up to negative 24x. Okay, now once again, I've got that scenario where I've got minus in front of plus. So I'm just going to put the minus signs in my answer because I know that's what the signs have to be. And now I'm not going to worry about putting negatives in here. So let's just think of it in a positive way. What are the factors of 72x squared that add up to 27x? Well, that would be 24x times 3x. So when you find those 2 factors, fill in your other squares. And now look for the 4 GCFs that will represent your factoring. Okay, top row, GCF is 2x. The bottom row, the GCF is 3. This first column, the GCF is x. And this second column, the GCF should be 12. And so it doesn't really matter what order you put these in. I could do x minus 12 and 2x minus 3, or I could switch these binomials completely because of the commutative property. So that's your answer for number 30. So practice this box method. Here it is again. Now this time I do not have minus in front of plus, so I can't just automatically put the 2 subtraction signs in my answer. Excuse me. So first of all, once again, it's very repetitive, but do you see a GCF? And no. So now, since A is greater than 1, let's use the box method. And I'm going to put first and last. I'm going to multiply those together. If you multiply 5y squared times negative 32, that's negative 160y squared. Okay, now I need the factors of negative 160y squared that will add up to positive 12y. Okay, so you're going to have to think about this one just a little bit. Run through all the factors of negative 160y squared, but hopefully you'll eventually come to 20y times negative 8y. When I multiply those together, I will get negative 160y squared. When I add these together, I will get positive 12y. So these factors, 20y, negative 8y, go in the other squares, and it doesn't matter what order. You could have switched those. Now you got the easy part. Find your 4 GCFs, and you'll have your answer. GCF of the top row, 5y. The GCF of the bottom row, just keep in mind that if both of your numbers that you're trying to find the GCF of are negative, then that makes the GCF negative. Okay? So for example, here they're both negative, so the GCF is going to be negative 8. All right, going this way. Notice one of the factors is positive and the other one is negative. So the only time the GCF will be negative is if both of the terms are negative. So they're not both negative here, so the GCF has got to be positive. Okay, so my GCF for this first column will be positive y. And then for this second column, the largest number that goes into both 20 and negative 32 would be 4. Okay, so here's my final answer. 5y minus 8, y plus 4. And once again, let's just run through FOIL just to make sure you understand how you can make sure you got the right answer. First terms together, outer terms together, inner terms together, last terms together, combine like terms with these linear terms. And sure enough, we got the factoring because we just found another way of representing this trinomial using multiplication. Okay, let's try this one. Another one using the box method. Is there a GCF? Doesn't look like it, so I'm going to say no. Okay, so let's create our little box, and hopefully you'll practice this enough to where this will be really easy. It comes in handy when the factoring gets a little tough. First and last, okay, multiply these together, and when you multiply 28k squared times negative 6, that's negative 168k squared. Now, and this is kind of tough, and you'll have to do some searching. What are the factors of this, negative 168k squared, that add up to 13k? And I'll help you out a little bit. That would be 21k times negative 8k. So those go in the other squares. It doesn't matter which order. Okay, find your GCFs. The GCF here of 28k squared and 21k, that would be 7k. Remember, these are both negative, so my GCF is going to have to be negative. That would be negative 2. Okay, looking here, the GCF of these, since they're not both negative, the GCF will be positive 4k. And then here, again, the GCF is going to have to be positive, and it should be 3. So my factoring, here's one binomial, 7k minus 2. And the other binomial will be 4k plus 3. And you can use the FOIL method and check it out, make sure it's right. Okay, this one is does have a GCF. Remember, that's the first question to ask. Actually, it doesn't have a GCF. I'm sorry. So we're going to say no. You could use the box method here, and you would be fine, but I'm hoping that you recognize this situation, that This is known as a perfect square trinomial. And I'm sure you were exposed to these in Algebra 1. What makes this a perfect square trinomial? Well, one of the things is if you look at the first term and you look at the last term, they're both perfect squares, meaning they both have perfect square roots. The square root of the first term is just 2n, and the square root of the last term is 5. Okay? Now, if you did a little extra, this is one of the things that makes this a perfect square trinomial, but there's something else. If you multiply these together, 2n and 5, you get 10n. Well, what happens if you double that? You get 20n. So if you can recognize perfect square trinomials, they're really nice to factor because we can show the factoring like this. 2n minus 5, the minus comes from the sign in front of the linear term. Or if you use the box method, you just ended up with this, which is okay as well. But if you can recognize perfect square trinomials, you can breeze through the factoring very easily. But I will accept either one of these. This would have come from the box method. This would have come from just recognizing how to factor this special case called a perfect square trinomial. And in addition to the perfect square trinomial special case, we also have this special case known as the difference between two squares, two perfect squares. And it only applies to the difference, the way we factor these. Okay? So when I recognize two perfect square terms being subtracted, immediately I'm going to write two sets of parentheses. These are going to be two linear binomials. These are really nice if you recognize them, and this comes up a lot in the future, so hopefully you'll recognize how to do this going forward. What I'm going to do is write the square roots of each term. Square root of c squared is c. Square root of 64 is 8. And then it makes it really nice to finish off the factoring. One of these has to be plus, and one of these has to be minus, and it doesn't matter which. You could switch the signs. But this represents the factoring known as, the special case known as the difference between two perfect squares. Okay, so hopefully those will help for the rest of the problems that you have to do. And if you're still struggling with factoring, it's so important for what we're going to be doing in the next few sections. So make sure you understand it. If you're needing extra help, come by and see me, and I'll be glad to help you.